Welcome. Today we're diving deep, really deep, under the hood of MySQL to figure out what makes it so mind-bogglingly fast. It all comes down to a structure that answers one massive question. Seriously, think about that. How does it work? It feels like straight-up magic, right? You ask for one specific thing out of a sea of a billion records and it just finds it instantly. Well, that's the core problem every high-performance database has to solve. And I'll tell you right now, it's not magic. It's just some seriously brilliant engineering. So, here's our game plan. First, we're going to reveal the engine's big secret. Then, we'll get into the actual blueprint of the B+ tree. After that, we'll look at the two big ways it's used, clustered versus secondary indexes. Then comes the really critical part, a choice every architect has to make. And finally, we'll talk about how to keep this whole system tuned for absolute peak performance. Remember that brilliant engineering I mentioned? Well, it's all built around one incredibly clever data structure, the B+ tree. This thing right here, this is the unsung hero, the true backbone of InnoDB's speed. And if you really want to unlock performance, you've got to understand how it works. All right, let's crack this thing open and take a look at the blueprint. Getting a handle on this core design is, without a doubt, the key to building database systems that are not just fast, but also scalable and efficient for the long haul. So what in the world is a B+ tree? Okay, yes, technically it's a self-balancing tree structure. But you know what its real genius is? It's obsessed with one thing, doing as little work on the slow disk as possible. See, reading from computer memory is lightning fast. Reading from a physical disk? Oof, that's slow. The B+ tree is designed from the ground up to minimize those slow disk reads. That's its entire reason for being. The easiest way to picture it is like a super efficient index for a massive encyclopedia. The top levels of the tree, the internal nodes, they're just signposts. They don't have the answers. They just point you in the right direction, saying, go that way. But the bottom level, the leaf nodes, that's where the good stuff is. That's where your actual row data lives. Now, because each node is a pretty big 16 kilobyte page, it can hold a ton of these signposts. We call that a high fan-out, and it's what keeps the whole tree nice and short. And the real killer feature? All those leaf nodes at the bottom are connected to each other, like a linked list. So if you need to do a range query, like get me all users between A and C, the database doesn't have to go back up the tree. It just zips sideways across the leaf nodes. It's incredibly fast. Okay, so InnoDB has this amazing B+ tree blueprint. What it does is really clever. It uses that same blueprint in two very different but connected ways. This is where we get into the all-important ideas of clustered and secondary indexes.
Now, if you only remember one thing, make it this. The clustered index, which is built on your table's primary key, isn't just a file that points to your data. It is the data. The leaf nodes of this B+ tree physically hold your full rows. The table is the index. A secondary index, on the other hand, is a totally separate B+ tree. It's like a different path to your data. Its leaf nodes store whatever you indexed, like a username, but they also store a copy of the primary key. That key is just a pointer telling the database where to find the full record in the main clustered index.
And that design has a huge impact on performance. When you search using a secondary index, let's say you're looking up a user by their email address, the database actually has to do a two-step lookup. First, it goes through the secondary index B+ tree to find that email and grab the associated primary key. Then, it takes that primary key and does a second search, this time in the main clustered index, to go find the full row of data. That two-hop process is exactly why searching by a primary key is always going to be the fastest way to get your data. Now, that whole two-hop thing, where the secondary index needs a copy of the primary key to point back to the main table, that leads us to what is probably the single most important design choice a database architect can make, a choice with absolutely massive performance implications. We're talking about picking a wide versus a narrow primary key. The ripple effects of this one choice are just staggering. A narrow key, like a simple 8-byte bigint, is small. That means more of them can fit into each 16 KB page, which gives you a higher fan-out and a shorter, faster tree. But here is the real kicker. That primary key gets copied into every single one of your secondary indexes. A narrow key keeps all your other indexes nice and trim. A wide key, like a big UUID, does the exact opposite. It bloats every single secondary index, making all of your B+ trees deeper, slower, and forcing way more disk reads for almost every query you run. Let's put some real numbers on this. Say you have a table with 1,000,000 rows, and you use a nice, narrow big int for your primary key. The B+ tree for that table is probably going to be just 3 levels deep. That means to find any single row, it's 3 disk reads max. That is incredibly efficient.
Now watch this. Take that exact same table, but switch to a wider UUID for the primary key. All of a sudden, your tree is now 4 levels deep. Now, one extra level might not sound like a big deal, right? But it is. That's a 33% increase in disk I/O for potentially millions of queries over the lifetime of your application. It's a massive self-inflicted performance penalty, all from just one design choice.
So what's the verdict here? What's the takeaway? Well, for the vast majority of applications, the answer is crystal clear. You should almost always default to an auto-incrementing integer key. The performance gains you get from a key that's narrow, always increasing and never changes, they are just too big to pass up. It keeps your main table neat and tidy, and all your secondary indexes lean and lightning fast.
Of course, a great initial design is just the start. Over time, even the most perfect index can fall victim to a really common performance thief: fragmentation. So let's talk about how to keep that monster in its cage.
Look, fragmentation is just a natural part of life for a busy database. When you insert keys all over the place, like with a random UUID, the database has to literally split a full page in half to make room. Now you have 2 pages that are only half full. Deleting rows also leaves empty holes everywhere. Over time, all this wasted space adds up, both on your disk and in memory, and that just makes your queries slower. But the good news is, we can totally fight back. Your best defense is a good offense. Using sequential keys like auto-increment in the first place prevents most of those nasty page splits. For tables that are already fragmented, you can periodically run optimized table. Think of it like a defragmenter for your hard drive. It just rebuilds the index and packs all the data in nice and tight again. And for really intense, write-heavy systems, you can even tune a setting called InnoDB fill factor, which basically tells the database to intentionally leave a little bit of wiggle room on each page for future updates.
At the end of the day, your database's speed is never an accident. It's a direct result of the choices you make about your primary keys, your indexes, and how you maintain them. The B+ tree is an amazing, powerful tool, and now you know how it really ticks. So the only real question left is, are you going to actively design for performance, or are you just going to leave it up to chance? Thank you for joining this Explain.